We will now extend the notion of convolution to certain types of distributions. So, convolution of distributions. So, obviously we will try to copy what we did for functions, and therefore we need to establish some notation which we used for functions. For instance, if you have u from Rn to R is a function and h is a vector in Rn, then we introduced what is tau h of u. Tau h of u evaluated at x is u of x minus h. Okay. So, from this you can easily follow the following relations. So, and now we define another notation, namely u chesh, I call this u chesh, the inverted hat of y is u of minus y notation. So, now you can, for instance, if you take tau x of u chesh evaluated at y, this will be tau x of u evaluated at minus y, this is u evaluated at minus y minus x, this is u chesh evaluated at y plus x, and this is equal to tau minus x of u chesh evaluated at y. So, you have tau x of u chesh is equal to tau minus x of u chesh. Okay. And the other one is very easy to verify. If tau x, tau y, if you compose, this is nothing but tau of x plus y. Okay. So, we have these notations. So, if u and v are two functions locally integrable, for instance, so let us take integral over Rn of tau x of u into v dy. So, this is equal to integral u of y minus x vy dy integral over Rn. So, then we make a change of variable y minus x equals z, and therefore, this is integral over Rn of u of z v of z plus x. Okay. So, v of x plus z dz by the change of variable formula, and this will turn out to be integral over Rn of u into tau minus x of v dz. Okay. So, you copy this, and therefore, we define the translation of a distribution. So, definition. So, we have tau x, so t belongs to d prime of Rn and x belongs to Rn. So, then we define the translation tau x of t acting on any phi. So, this is for every phi in d of Rn. So, if you look at what we have done here, imagine instead of u you had t. So, this is nothing but t of tau minus x of phi. Okay. So, this is the definition. Now, it is clear if phi n goes to 0 in d of Rn, then tau minus x of phi n will also go to 0 in d of Rn. You can easily verify that because they are just translations by a single vector x, and therefore, all the supports will be contained in a fixed compact set, which is the translation of the original compact set by x, and then all the derivatives will go to 0 uniformly. There is no problem about that. So, this defines a new distribution. So, tau x t is a distribution which is defined this way. Now, if u and v are two functions for which, if they are L1 functions for instance, so uv say in L1 of Rn, then what is u star v of x? This is equal to integral over Rn of uy v of x minus y dy, and this is equal to integral over Rn of uy v chesh of y minus x dy, and that is equal to integral uy tau x of v chesh at y dy. So, if we copy this, given t in, so definition again, t in d prime of Rn and phi in d of Rn, then we define t star phi is a function, not it is a function on Rn given by t star phi at any point x is equal to t acting on tau x of phi chesh. So, again if phi n is a sequence which converges to 0, then tau x of phi chesh is also a sequence converging to 0 in d of Rn, and so this defines therefore t of that will go to 0, and therefore this defines a well defined function. Okay. So, now before we go to examine the properties of the convolution of a distribution and a C infinity function with compact support, we need a following technical lemma. Okay. So, let phi belong to d of Rn and ei in Rn be the ith standard basis vector. So, ei will be 0 etc., 1 in the ith place, 0 elsewhere. Okay. So, this is ith standard basis vector. Then phi minus tau of h ei phi by h goes to d phi by dxi in d of Rn as h goes to 0. So, proof. So, phi minus tau h ei of phi, this is just a translation of phi by h ei, h is a number, real number, and therefore these are all d of Rn functions, and so if you have so this belongs to d of Rn, no problem, and if you have that h is sufficiently small, so h sufficiently small, all supports in a fixed compact set. Okay, whether for all h as h goes to 0. Okay. So, now you take phi minus tau h ei of phi divided by h, what is its value at x? This is equal to d phi, okay, sorry, minus d phi by dxi of x. Okay. Now, this is nothing but phi of x minus h ei divided by h. Therefore, by the mean value theorem, this will be equal to d phi by d xi by dxi minus d phi by dxi at x, okay, where xi is a point in the line segment joining x and x minus h ei. Okay. So, this is just a mean value theorem. Now, all derivatives of phi are compactly supported, and so uniformly continuous. Therefore, given any epsilon greater than 0, there exists a delta positive such that mod h less than delta and implies mod x minus xi is also less than delta, and you have mod phi minus tau hei of phi by x minus d phi by dxi of x is equal to mod d phi by dxi at xi minus d phi by dxi of x, and that is less than delta epsilon, because xi minus x is less than delta. So this shows that phi minus tau h ei of phi by h converges to d phi by dxi of uniformly. Similar proof for all its derivatives. And therefore, they all have compact same support in a fixed compact set, and therefore you have that this implies that phi minus tau h ei of phi by h goes to d phi by dxi in d of r. So this completes the proof of this lemma. Okay, so now we have the following theorem. Let T belong to d prime of Rn and phi belong to d of R. Then we have the following. We have for any x in Rn, we have tau x of t star phi equals tau x of t star phi equals t of t star tau x of phi. So this tau x can be moved anywhere to either component in the convolution. Okay. 2. For any alpha multi-index, d alpha t of t star phi, d alpha of t star phi equals d alpha t star phi equals t star d alpha phi. So again you can take any derivative exists, and the derivative can be pushed to either differentiate the distribution or differentiate the function. So in particular, t star phi belongs to C infinity of Rn, which in our notation is of course E of Rn. Okay. So 3, if psi is also in D of Rn, then you have t star phi star psi is equal to t star phi, t star phi star psi. Okay, let us check that this has a meaning. T star phi is a C infinity function, psi is a C infinity function with compact support, so you can of course define the convolution of these two. Here phi and psi are both C infinity functions with compact support, therefore the convolution is also a C infinity function with compact support, and therefore I can convolve it with a distribution that is well defined by what we have seen. Okay, so and this shows some kind of associative law. So 4, this will be a useful result later on. If t star phi equal to 0 for all phi in D of Rn, this implies then t equals 0. So it is only the 0 distribution. So, proof. So, first, so you take tau x of t star phi, evaluate it at any y, this is equal to t star phi at y minus x. Okay, and how is this defined? This is t of tau y minus x phi chesh. That is the definition of the thing. Now, tau y minus x I can write as tau y tau minus x, and that is commutative. Okay, so this is, I can compute it in two ways. So, this is tau t of tau minus x tau y of phi chesh, which is tau x of t acting on tau y of phi chesh, and by definition this is tau x of t star phi evaluated at y. But this can also be written as t of tau y tau minus x phi chesh. Now, tau minus x phi chesh is nothing but t of tau y, we have already seen this, tau x of phi chesh, and therefore this is nothing by definition, is nothing but t star tau x of phi evaluated at y. So, this is, the two are equal. So, that proves the first statement. Second one. So, we will prove it, let alpha equal to 0, 1 in the ith place, 0 elsewhere. We will prove it for one derivative, namely d by dxi, and then we will iterate it to get for any other derivative. So, let us take d by dxi of t star phi of x. So, this is limit as h goes to 0, if this limit exists, of course, t star phi of x minus t star phi of x minus hei divided by h. This is a usual definition of a derivative. This is equal to limit h going to 0, 1 by h of t star phi of x minus tau of hei t star phi of x. So, now of course, we have the choice of pushing the t of tau star h wherever we like. So, we have limit h tending to 0, 1 by h t star phi minus tau hei of phi, okay, evaluated at x. And then we saw that this goes to what is this definition? So, limit as h goes to 0 of t of tau of tau x of phi minus tau hei phi over h chesh. That is the definition of the convolution of a function. But we saw that this function here goes to d by dxi as in d of Rn. So, tau x also will do that, and therefore, this is nothing but t of tau x d phi by dxi chesh, and that is nothing but t star d phi by dxi evaluated at x. So, we have shown that the limit exists, and in fact, the derivative is equal to this. Now, we can take the tau in another way also. So, we can also have the d by dxi of t star phi at x. Okay, before I do that, so by the same lemma, so this is by lemma. So, by the lemma again, we also have phi minus tau of minus HEI phi by h. Now, this will go to minus d phi by dxi because you are taking the difference quotient in the opposite direction. Tau of minus HEI will be phi of x plus HEI. So, phi of x minus phi of x plus HEI by h will go to minus d phi by dxi by the same lemma. Okay, so therefore, in d of Rn. So, d by dxi of t star phi at any x is limit h going to 0. Now, I will take the tau in a different place. So, this tau can be pushed, we pushed it to the phi earlier, now we will push it to the t. So, this will be equal to t minus tau HEI of t by h star phi. That is equal to limit h going to 0 of t minus tau HEI of t by h acting on tau x of phi chesh, which is equal to limit h tending to 0 of t acting on tau x of phi chesh minus, so we are taking the translation of t, this is minus tau of minus HEI of tau x of phi chesh by h. And just by our remark, we just saw that this is giving you minus t d by dxi of tau x of phi chesh by the lemma and remark above. But what is this? Minus t of d by dxi is nothing but dt by dxi acting on tau x phi chesh, and this is nothing but dt by dxi star phi evaluated at x. Therefore, you have d by dxi of t star phi equals d by t star d phi by dxi equals dt by dxi star phi, and now you iterate to get to, for all multi indices, alpha. So you see, you can push the derivative wherever you like, and in therefore it makes it a C infinity function because you have just shown that. So now we have to prove the third one. Third one is a little sticky, so let us carefully do it. Okay. So phi psi in D of Rn. Okay, so we want to show T star phi star psi at any x is T star phi star psi at any x. Now we can replace tau x psi by tau minus x psi, because that is also a C infinity function with compact support. So enough to prove and use 1. So enough to prove T star phi star psi at 0 equals T star phi star psi at 0, because once you prove at 0, the value at any x is just tau of minus x at the value at 0, and the tau minus x can be pushed anywhere. So, in particular, you can push it to psi and use it by the previous theorem. It is so, this is, it's enough to prove this. So, just check that. Okay, so let us take, so T star phi star psi evaluated at 0. What is this? This is T acting on tau of 0, which is the identity of phi star psi chesh. So, let us see what is this phi star psi chesh. You evaluate this at any x, this is nothing but phi star psi evaluated at minus x, and that is equal to integral over Rn of phi of minus x minus y psi y dy. So, now I will change y to minus y. Okay, so this is equal to integral Rn minus phi of z minus x psi z dz. No. Okay, so this is equal to let me write it a little clearer. So, this is equal to minus x plus y psi chesh y, and I can write this as phi chesh of y minus x. X minus y, x minus y. Okay, so I will write this as phi chesh of x minus y. So, this is equal to integral over Rn tau y of phi chesh at x and psi chesh of y dy. So, sorry for that. Okay, so I made a change y to minus y. So, then I wrote it in a slightly different form. Okay. So, now we are going to, this integral suffices to consider the integral over the compact set which is support of psi chesh. Okay. Then integral is the limit of the Riemann sums. So, you have, I am going to take the integral lattice points, okay, with epsilon as the mesh size. So, this will be, each cube has volume epsilon power n into sigma over all lattice, integral lattice points p tau of epsilon p phi chesh of x psi chesh of epsilon. Okay, so this is, I am just replacing it as a Riemann sum, evaluating at all these points which are the integral. Okay. Now, so P equals integral lattice point. But support psi chesh compact implies this is a finite sum, because it is a compact set. So, only finite number of integral lattice points will be there, all the others this will be 0, and therefore, I can just ignore them, and therefore, this is essentially a finite sum. And then both phi and psi are bounded, they are of compact support. So, they are bounded and uniformly continuous. and therefore convergence of Riemann sum to integral is uniform in X. Similar argument for any derivative of phi star psi chesh. So, you can change, because the derivatives of phi star psi, you can push the derivative to any one of them and then apply the same argument. Therefore, you have that phi star psi chesh is the limit as epsilon goes to 0 of epsilon power n summation over all lattice points p, and this only a finite sum, psi chesh of epsilon p into tau of epsilon p of phi chesh in d of r. So, once you have this convergence, then I have to take T of that. Therefore, T of T star of phi star psi at 0 is nothing but T of phi star psi chesh, and because that is given by this limit and this is essentially a finite sum, so I can take T into that. So, therefore, this is equal to limit as epsilon goes to 0, epsilon power n sigma over p of T of tau epsilon p phi chesh into psi chesh epsilon p. So, and that you can now write, this limit is going to be an integral where you replace epsilon p by y. So, this is nothing but integral T star T of tau y phi chesh psi chesh of y dy over Rn, and that is equal to integral T star phi of y psi of minus y, and that is nothing but the usual convolution. So, T star phi star psi evaluated at 0. Okay, so you use psi of 0 minus y, so that is just evaluation of this. So, we have proved this formula, T star phi star psi 0 is equal to T star phi star psi 0, and therefore that completes the proof of the third part. Okay, and now for the fourth part. So, let us T in d prime of Rn and T star phi equal to 0 for all phi in d of Rn. Okay. So, now you phi, let us say phi tilde. Okay. So, for all phi tilde in d of Rn, phi tilde chesh is also in d of Rn. Therefore, 0 equals T star of phi tilde chesh in particular at 0, and that is nothing but T of phi tilde, because it is 0 everywhere. So, it is in particular 0 at 0, and that is precisely the formula is tau 0 is identity, and you have to take chesh twice, and therefore you get T of phi tilde. So, this means for every phi tilde you have T of phi tilde equal to 0, and therefore you have that T is identically 0. So, this shows the thing. So, now we will continue with this next time.